Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Klepner and Kolenko. We will continue to discuss topics from Chapter 2, Newton's Laws. What we are going to do today is we'll pick up a couple of examples of rotational motion and we will analyze the motion using Newton's laws within the framework of polar coordinates. Now, one thing you have to remember, especially while writing the force equation, is that acceleration, being the rate of change of velocity, will have two components. Velocity is a vector. It has both magnitude and direction. So you could have acceleration due to change in magnitude of the velocity or change in speed, as well as acceleration due to change in direction of motion. For example, if you are considering an object which is moving in a circle, even if the magnitude of the velocity is constant, look at each point, the direction of velocity is going to be different. So purely due to change in direction, you could have an acceleration in the tangential direction. So in the first example, we will take a very simple case of an object having only radial acceleration. So this is a block which is attached to a string. So a block of mass m rotates with constant speed v at the end of a string of length r as shown in this figure. Find the force on the mass in the absence of gravity or friction. Okay. Now first thing, identify what are the forces acting on the object. There is no gravity, which means you can neglect the weight. So the only force acting on the object is the spring force or tension, which you call it as T. And what is the direction of tension? So usually tension acts towards the center in the inward direction. Okay. So now after identifying the forces, you can draw the force diagram. So we can imagine that the object is a point mass of mass m. Then the force T is acting in the inward direction, and by invoking the polar coordinate system you can easily make out that the tension T is acting in the radial direction, right? So the relevant acceleration is going to be radial acceleration, because what is the direction of the force? The acceleration also going to be along the same direction. And from the previous class, we have derived the expression for radial acceleration as AR equal to R double dot minus R theta dot square. And by convention, the inward direction is taken to be negative. So the string force or tension is given by minus T R cap. You can write down the radial equation of motion. F is equal to ma, force is minus T, which is equal to m into acceleration, which is AR. So this is m into R double dot minus R theta dot square. Now remember, we are talking about a circular motion, and in the case of a circle, the radius is a constant. So R is essentially a constant, which means R double dot is going to be 0. Also, if you look at this term theta dot, and what's the meaning of this? This is d theta by dt, which is known as angular velocity omega. Remember, in the case of linear motion, if x is the displacement, rate of change of displacement dx by dt you call as velocity, or linear velocity to be precise. Now in the case of angular motion, the displacement is measured in terms of angle theta. So rate of change of displacement here is d theta by dt, which is nothing but the angular velocity. And the angular velocity theta dot and linear velocity v are related through this equation theta dot equal to v by r. I'm sure you are already familiar with this relation. Okay. So now I can write the radial acceleration in terms of the angular velocity as AR equal to minus R theta dot square, which is minus R V by R whole square, or minus V square by R. So now substitute this back into this equation. You have T equal to minus M into AR, which gives you T equal to mv square by R. So this is the expression for the tension. So if you take the case of a man who is doing a hammer throw, this is similar to the case we have discussed here. So the hammer is going to experience a tension towards the center in the inward direction, and by Newton's third law, the person is going to experience an equal and opposite force in the outward direction. In either case, the tension here, which is the only force acting in this case, this is going to provide the necessary centripetal acceleration or centripetal force which makes the circular motion possible. Imagine if there was no tension or no centripetal force, what happens? Look at the direction of velocity. Velocity is always tangential, which means the object has a tendency to move in a straight line along this direction. But since you have a centripetal force or tension acting inward at every point, the velocity component is going to bend. So as a result of this continuous bending, instead of a straight line, it's going to go through a circular path. So tension here acts as the source of centripetal acceleration. So this is a simple example where we had only the radial acceleration. Let's move on to another example where we have both radial and tangential components for acceleration. So imagine that you have a block of mass m rotated at the end of a string of length r. The motion is in a vertical plane in the gravitational field of Earth. The forces acting on the m are weight W, which always acts downwards, and the tension on the string, which acts towards the center. The instantaneous speed is v, and the string makes angle theta with the horizontal axis. Find tension and the tangential acceleration at this instant. So once again, you have an object of mass m which is tied to a rope, and it is executing a circular motion. Let r be the radius of the circle. And here there are two forces acting. One is the weight acting in the downward direction, and also you have the tension acting towards the center. So as I said, here we are going to have two kinds of motion. One is the radial motion and second one is the tangential motion. So having identified the forces, it's time now to draw the force diagram. So you can represent the object with a point mass of mass m. And what are the forces acting? You have tension acting in the inward direction towards the center. Assume this is the center. And weight acting in the downward direction, and the tension or the string makes an angle theta with respect to the horizontal. Okay. So by invoking the polar coordinate system, you can identify that tension is acting along the radial direction. Okay. Now from this geometry, imagine this is a triangle. This angle is theta, and this angle is going to be 90. So the third angle is going to be 90 minus theta, and if this is 90 minus theta, this is going to be theta. Okay. Now the weight which is acting in the downward direction, I can decompose this into two orthogonal components. One component along this direction, which is the tangential direction, and another component along the radial direction, this direction. You know how to decompose a vector, right? So this component is going to be W cos theta, and this component is going to be W sin theta. And by convention, all the inward direction or downward direction are taken as negative. Oh. So let's first talk about the radial motion. What are the radial forces acting? We know that T is acting in the inward direction, so this is minus T. And you also have a component of W sine theta acting in the inward direction. So this is minus W sine theta. And what is the corresponding acceleration? You have radial acceleration AR given by R double dot minus R theta dot all square, as we had derived in the last class. So the radial equation of motion is going to be F is equal to MA. F is minus T plus W sine theta, which is equal to M into AR, that is R double dot minus R theta dot all square. As in the previous case, we are talking about circular motion. Radius is a constant, so R double dot vanish and you have AR equal to minus R theta dot square, which is nothing but minus V square by R. So you can rewrite this equation in terms of the angular velocity. So substitute for AR in this expression and rearrange the terms. You get T equal to mv square by R minus W sine theta. And from this expression, you know that the tension is going to vary as a function of theta. And what is the maximum value of theta? It happens when theta equal to 90 degrees. So W sine theta is going to reduce to W. So the maximum value of tension is, the minimum value of tension is T equal to mv square by R minus W. Now remember this term mv square by R, this is nothing but the centripetal acceleration or the centripetal force which makes the circular motion possible, and W is the weight which acts downward. So we need always make sure that mv square by R is greater than W. If this condition is not satisfied, what happens? The weight is going to overpower the centripetal acceleration, and as a result of that, the mass is not going to follow a circular path, but it starts to fall down. So always make sure weight is less than mv square by R. Now moving on to the tangential force. So what are the tangential forces acting? Tension is acting along the radial direction. It has no component along the tangential direction, so you don't have to consider this. You have only a component of W cos theta acting in the tangential direction. Since this is in the downward direction, you can consider it to be negative. So minus W cos theta is the only force. And what is the corresponding acceleration? In the previous class we have derived the corresponding acceleration. A theta is R theta double dot plus 2R dot theta dot. So you can write down the equation of motion, tangential equation of motion. F is equal to MA, force F is minus W cos theta. This is equal to M into acceleration A theta, which is M into R theta double dot plus 2R dot theta dot. Once again, since we are talking about circular motion, radius R is constant, so dr by dt or R dot equal to 0. So A theta reduces to R theta double dot. So putting it back into this equation, you get A theta equal to minus W cos theta divided by M. And here the mass does not move with constant speed, it accelerates tangentially. So you can see that acceleration depends on the angle theta. So when the object is at this position, theta equal to 0, cos theta equal to 1. At this position, when it is having an upward swing, here theta equal to pi by 2 and cos theta equal to 0. Once again, when you have a downswing at 180 degree, cos theta equal to minus 1. So if you follow the signs, you will find that on the downswing, the tangential speed increases. On the other hand, during the upswing, the speed is going to decrease. So that's the case of rotational motion, which has both tangential and the radial components. Let's now scale up the problem. Take a problem where in addition to radial and tangential motion, you also have a constraint condition. Okay. So this is the case of a whirling block or a rotating block. So imagine a horizontal frictionless table has a small hole in its center as shown in this figure. Block A on the table is connected to block B, which is hanging beneath, through a string of negligible mass which passes through the hole at the center of the table. Initially, B is held stationary and A rotates at constant radius r0. So r0 is the radius of this circle with a steady angular velocity omega naught. If B is released at t equal to 0, what is the acceleration immediately afterwards? So first thing, we need to identify what are the forces acting on body A and body B. So in the case of body A, it is moving on the surface of the table, which means motion is confined to this horizontal plane. There is no vertical motion. In other words, the vertical forces are balanced, so we need not consider the vertical direction at all. And the only force acting in the downward direction is the tension through the string. Okay. And when it comes to B, what are the forces acting? B is hanging on this rope, so obviously the tension of the string is going to act on B. Similarly, B has a certain weight WB which acts in the downward direction. So tension and weight here, only tension here. So once you identify the forces, it's time now to draw the force diagram. So you can represent object A with a point mass having mass MA, and tension as always act in the inward direction towards the center. And from the polar coordinate system, you can notice that tension is acting along the radial direction. So you can call theta as the angle between the tension as well as the horizontal direction. When it comes to object B, you can represent it with a point mass of mass MB. There are two forces acting, tension in the upward direction and weight in the downward direction. And you can choose this vertical direction as the Z coordinate. Let's write down the equations of motion. First, for object A, F is equal to ma. Force is the tension acting in the inward direction, so F is minus T, which is equal to ma into the radial component of acceleration, which is r double dot minus r theta dot square. Writing down the tangential equation of motion, as you can notice, there is no tangential force acting on this object, so tangential force is 0 equal to mass into tangential acceleration, which is r theta double dot plus 2r dot theta dot. So these are the equations of motion for object A. And what is the equation of motion for object B? Here the motion happens along the z direction, so this is a linear motion, and the forces are plus t in the upward direction minus omega b wb in the downward direction. So t minus wb equal to mass mb into acceleration z double dot, but here the movement is in the downward direction, so acceleration is going to be minus z double dot. You can multiply this equation throughout with minus 1, so it becomes WB minus T equal to MBZ double dot. So this is the vertical equation. So in addition to these equations of motion, you can also derive a constraint equation. What is the constraint here? Just like the examples we discussed in the last class, here also the length of the rope is a constant, right? So if you take L as the length of the rope, you can write L equal to this height, which is Z, plus this radius, which is R. constant equation, just like the equation of motion, has to be a second order differential equation. So you can take the derivative with respect to time twice. So derivative of L is going to be 0. So you have R double dot equal to minus Z double dot. Now using this result, you can rewrite equation 1. So in equation 1, I have R double dot. So instead of that, you can put minus Z double dot. So it becomes minus T equal to MA minus Z double dot minus R theta dot square, or equal to MA Z double dot plus MA R theta dot square. Similarly, from equation 3, you have WB minus T equal to MBZ double dot, or T equal to WB minus MBZ double dot. So you have two equations for the tension, which means you can equate these two and write MAZ double dot plus MAR theta dot square equal to WB minus MBZ double dot. So you can bring this term to the left hand side and this term to the right hand side. So you have MAZ double dot plus MBZ double dot equal to WB minus MAR theta dot square. And what's our aim? Our aim is to calculate the acceleration of the block, which is nothing but Z double dot. So from this equation, Z double dot is W minus MAR theta dot square divided by MA plus M. Now we are asked to calculate the acceleration at time t equal to 0 when the block B is detached from the rope. So even though the acceleration changes instantaneously, the velocity and position do not change. So immediately after the object B is released, R is still R naught and theta dot is still omega naught. So acceleration at time t equal to 0, Z double dot 0 is WB minus MA. Instead of R, I have R naught. Instead of theta dot square, I have omega naught square divided by MA plus MP. Coming to the final example, probably the most popular one, and this is a conical pendulum. I'm sure you are familiar with a simple pendulum. A simple pendulum is a harmonic oscillator which oscillates along a line or which executes linear oscillations. On the other hand, conical pendulum executes circular oscillations. Okay. So as shown in the figure, you have a mass M which hangs by a massless rod of length L, which rotates at constant angular frequency omega as shown in this figure. The mass moves with steady speed in a circular path of constant radius. Find the angle alpha which the string makes with the vertical. Now here I have a typo. Instead of angular frequency, this should have been angular velocity. Okay. First thing first, identify what are the forces acting on this object or bob. So obviously you have weight acting in the downward direction. Then you have tension acting along the string or rod towards the center. So tension and weight are the two forces acting. Now draw the force diagram. So you can replace the bob with a point mass of mass M and weight acting in the downward direction and T acting in the upward direction along the rod. And here alpha is the angle between the string or the rod and the vertical direction. So alpha is the angle between T and the vertical. T being a vector, I can decompose it into two components. A vertical component, this is going to be T cos alpha, and a horizontal component, this is going to be T sin alpha. By convention, Right hand direction is taken as positive and left hand direction is taken as negative. So this is going to be minus t sine alpha. Now let's write down the equations of motion. First, we have the vertical direction or the y direction. So write down the corresponding equation of motion. And what are the vertical forces? I have t cos alpha in the upward direction and minus w in the downward direction. So t cos alpha minus w equal to, what is the acceleration? Look at the motion here. The bob is moving along a circle and circle is confined to a single plane, right? Which means there is no vertical movement. Consequently, the acceleration in the vertical direction is 0. So right hand side equal to 0. Let's now find out the horizontal equation of motion. So we have a bob moving in a circle, or the circle is confined to a horizontal plane. So I can consider two components here. One is the radial component and one is the tangential component. But look at the force here. So I have a force t cos alpha acting in the radial direction. On the other hand, there is no force acting in the tangential direction. So even if I write the tangential equation of motion, that is going to be trivial. Okay, I cannot get any useful information from that. So I'm going to write down only the radial equation of motion here. So as I said earlier, I have t sine alpha acting towards the center, and by convention this is taken as negative. So minus t sine alpha equal to m into ar. Now the radial acceleration is r double dot minus r theta dot square. For a circle, radius is a constant, so r double dot is 0. Theta dot is angular velocity omega, so ar equal to minus r omega square. So my equation of motion is minus t sine alpha equal to minus mr omega square. And from this geometry, I can write sine alpha equal to r by l, or r equal to l sine alpha. So substitute for r in this equation, you get t sine alpha equal to ml omega square sine alpha. Sine alpha is common on either side, so you can cancel these two. You get tension T equal to ml omega square. Now using this result, you can rewrite the vertical equation of motion. Instead of T, you can write ml omega square. So the vertical equation of motion becomes ml omega square cos alpha equal to W. Weight is nothing but mass into gravity, mg, right? So ml omega square cos alpha equal to mg, or cos alpha equal to g by l omega square. So we are asked to find out what is alpha. Alpha is going to be cos inverse g by l omega square. Now what we will do is we will plot cos alpha as a function of omega. So this is how you get the solution. Cos alpha as a function of omega. Let's look at the two extreme endpoints. Okay, first here. As omega tends to infinity, you can see omega is in the denominator. So when omega goes to infinity, this term goes to 0. So cos alpha goes to 0. We know for what value of alpha, cos alpha goes to 0. This is for pi by. So what's the physical meaning of it? When omega goes to infinity, when the bob rotates at a very high speed, the angle alpha increases. Finally what happens? The bob is almost horizontal. So at high speed, the bob flies out until it is almost horizontal. Take the other extreme point, omega decreases, finally becomes 0. So as omega goes to 0, omega is the denominator, anything divided by 0 goes to infinity. So our solution predicts cos alpha tending to infinity. But we know that this doesn't make any sense at all, because any trigonometric function cos alpha, its maximum value is plus 1. right? So for any alpha, cos alpha has to be less than or equal to 1. So this is a problem. So mathematically this is not possible, but if I follow the geometry and apply all the physical principles I know, this is the value I am getting. So what we do is we need to do a more detailed analysis of a solution. So let's see what happens at the point cos alpha equal to 1. Because this is the, according to mathematics, this is the maximum value the alpha can attain. Right? So when cos alpha equal to 1, from this equation I can write g by L omega square equal to 1 or omega equal to square root of g by L. So this is a decisive point for me. Now our solution predicts that for all omega less than square root of g by L. Basically this side cos alpha is greater than 1, and at this point when omega equal to square root of g by L, then cos alpha equal to 1, and I know that cos square alpha plus sine square alpha, this is a fundamental trigonometric relation, this is equal to 1. So when cos alpha equal to 1, sine alpha equal to 0, and when sine alpha equal to 0, alpha equal to 0. And what's the meaning of alpha equal to 0? Remember, alpha is the angle between the vertical and the rod. When alpha equal to 0, it means that the bob is simply hanging vertically down. Now, what is the issue here? Why did we get this kind of an absurd result? During the derivation, we have overlooked one fundamental mathematical principle. From equation 3, when we arrived at equation 4, what did we do? We found out that sine alpha is common on either side, so we just divided this entire equation with sine alpha on either side. That's how we got this equation, right? But remember, at this point cos alpha equal to 1 and sine alpha equal to 0. So basically you are dividing an equation with a term whose value is equal to 0. Can you divide something with 0? No, right? So whenever we cancel same terms on both sides of an equation, it should be a non-zero value. So this is the mistake we have done. So we need to specify our solution now. So physically, for omega less than or equal to square root of g by L, we know that cos alpha cannot be greater than 1. So we are going to specify that the only acceptable solution is cos alpha equal to 1 and consequently alpha equal to 0. Similarly, for the other case, omega greater than square root of g by L. Basically this part of the graph here, as you can see from the graph, there are two solutions possible. One, cos alpha equal to 1, and 2, our original graph, cos alpha equal to g by L omega square. Now what's the meaning of cos alpha equal to 1? Here alpha equal to 0. So the bob is rotating rapidly but hanging vertically. This is a very unstable situation. So even if I have a slightest perturbation in the system, this is going to break down the motion completely. So I don't prefer this. On the other hand, what's the meaning of the second solution? The bob is flying around in circle at an angle alpha with respect to the vertical. This is a more stable condition. So physically, this is the solution I am going to prefer. So whenever you solve a physics problem, always remember the solution should be mathematically valid. Also, it has to be physically valid. That's for today. What we do in the next class, we will discuss about some of the forces which we encounter in our daily life and how to get meaningful interpretation of these forces using Newton's laws. Thank you.